Welcome, everyone. It's great to see everyone for this leadership lab with Krishna Shankar. Krishna is a computer vision engineer at Apple, based in Silicon Valley. Krishna and I have been friends since grad school. We were roommates in grad school, where he did a PhD in computational sciences. Which department were you in, actually, Krishna? I always forget. Was it
I was
CN?
in mechanical engineering.
Mechanical engineering. So he was in mechanical engineering at Caltech, where he built robots for space missions, particularly for the Mars rover missions. And then since then has done a lot of interesting things in a variety of tech labs and tech companies. He was at Google X, which is the kind of innovation lab based out of Alphabet, and he can talk a little bit more about that during the discussion. And then he was at Toyota Research, and worked at a startup, and now is at Apple. And he's one of the most thoughtful thinkers about what's really possible in AI, as someone who actually builds a lot of embodied intelligence systems. He thinks about these systems quite deeply, and I've really learned a lot by talking to him. So I'm really excited that he'll be talking today about the possibilities of autonomous driving and what's possible, and are we there yet? So with that, Krishna, over to you.
Yeah, thanks for the great introduction, Abhilash. Yeah, this is fairly informal, but yeah, I'm not sure if we want to take questions during. I'm okay with that, or we can also wait till the end. But let's see. What can you guys see? Can you see one slide or multiple slides?
We're seeing multiple slides now.
Okay. Maybe we will just do this view. Okay. All right. So the title of my talk is
By the way,
Yeah.
Krishna, we can't see the screen yet.
Okay.
Sorry.
Again. No worries. Okay. All right.
Yeah.
Okay. So the title of my talk is Self-Driving Cars. Are we there yet? And so the graphic below is an incident involving Cruise, which is General Motors' self-driving subsidiary, and they ran into a parked bus. And so I think the answer might be we're not quite there yet. We're still working on it, but so I'm hoping to give you some of my impressions and ideas of where this field is. Hopefully, tie it into other technology and innovation and how I think about those things, and hopefully give you some useful ideas as well. So self-driving is something that we've been thinking about now for a long time, and so the video shown here is an effort called NavLab, which was in Pittsburgh in Carnegie Mellon, and so that's in 1986, and they all the compute on that vehicle probably amounts to less than you have in your pocket at the moment. And so it's very old, but this problem of making a car drive itself has been fascinating people for decades at this point, and it's still a very interesting, rich, hard problem, as you'll see, and remains very hard. And so, I my view is that today across all technology ideas, things become viral. Things tend to a few ideas tend to become very, very popular, and I'm not exactly sure why, but I can imagine things like social media, where we all kind of talk about things in a public forum, maybe appeals to authority, where certain people have kind of an outsized voice and authority. And then also, I think in particular, the fear of missing out or the fear of not agreeing with the crowd can be very scary. And so it's always been very difficult for humans to be rational, and this has been true forever. But I think it's even harder now with these networks, and everyone's seeing what your opinion is, and you feeling like you maybe have to think or feel the same way. And so these aren't maybe good for innovation and progress. And I think the other challenge, machine learning is incredible. It's allowing us to do things that we've never been able to do before. But, maybe it's not perfect because it does allow you to get to maybe 70, 80% of performance for any given task, as long as you have the data, whether it's labeled or otherwise. And so this can give the impression that, we've solved things. And when in fact, we're from the perspective of adding value or delivering results in the real world, we're actually much further than we think potentially. And real progress is very slow, very hard, sadly. But this is the way it has been, will always be. And the key ingredients for progress are lots of time, lots of effort, and great collaboration with all sorts of people, and also maybe collaborating with people you've never met because of the work that's come before. And I think the impact of these technologies, especially today, is highly overestimated short term and underestimated in the long term. And so it's hard to predict the things that how the things that we work on today will impact us in the future. So to give you a little bit more background, I've been working in robotics and computer vision for since 2010. I don't want to think about how long it's been, but the first project I did was at Carnegie Mellon, where I worked on software for a lunar lander platform. And there you can see I was kind of trying to control its attitude or rotation. And then some of the other projects I worked on include this is a robot called RoboSimian. It's a quadruped over at NASA JPL. It's built to kind of go into human environments, disaster scenarios, and help out however it can. This is RoboSimian trying to climb into a golf cart very slowly and a bit clumsily. And this, some of my work there was to try to get this to be a little less clumsy. And so this is some algorithms we worked on to enable the robot to walk. And so we did a task where we had to walk over this structured pile of cinder blocks. And one of the things you learn working in robotics is that there's lots of successes. It's really hard, but then there's also failures that can be pretty catastrophic. And so one wrong step and you have a disastrous like the robot flips over, kind of like that, and you need to bolt the sensors back on, and not a great day, but part of the job. And then my first job out of school was I worked on a project, as Abhilash referred to, over at Google X, where a great team of people tried for many years to build a cheap, reliable home robot. And so you can see the kinds of things we imagine doing, where cutting vegetables, cleaning your toilet, making popcorn, everything you might want to do. I think the lesson was very clear. This is much harder than many imagine it is. And so great progress, great ideas, but not quite ready to ship to people and take their money. After that, I worked at Toyota, where we went a little bit more hardcore with a much more expensive robot. This robot has 27 degrees of freedom. When it stands fully erect, it's as big as Shaquille O'Neal. And this is the robot trying to get some groceries. You give it a list of groceries, it goes into the store and grabs everything. And it's a little bit about the stuff I worked on in the past. And as Abhilash mentioned, I currently work on the Apple Vision Pro. Part of the reason I want to do this is I felt that really touching reality first was something I'm very curious about. And so the robots I showed you in the previous slides on other planets, they do work in reality, but we often have to control them very closely and monitor them carefully. And there's only one of them. But I really am curious about what it takes to put a robot out into the wild, into the hands of people. And you could think about this as a robot that has no moving parts, but it's still doing a lot of things that a robot's got to do. For example, it's got to understand the world, what's around it, what you want to do. And you also have to be able to interact with it. And so this is this is currently what I'm working on. And so, but yeah, let's get back to our main subject here. We're talking about self-driving. Here's another little look into the past. So in 2005, there was, and I should say this is really what kicked off the explosion of self-driving that's happening now and was funded by DARPA, a US science funding agency. And so there's a challenge involving a handful, maybe 10 different university research lab and company teams to try to get cars to do things like driving in the desert or driving in cities autonomously. And I think people started to understand the challenges back then. So this is a video of the Caltech autonomous car, mostly going okay. All of a sudden it drives into the barriers, goes over the fence, and is about to run into a bunch of people. And so this is interesting. And I think at the time, the failure was that they had programmed the system such that if any one out of the many sensors they had went down, they had the code, the systems to be able to keep going. But they didn't take into account, well, maybe two sensors could go down. And so in this case, they lost GPS and they lost one of their cameras, and the software just didn't know what to do. So this is an exception, a very rare event, and thankfully no one was hurt. But yeah, this is a small preview of what's to come. And so at a high level, what are the components of a self-driving system? As you can imagine, you do need to be able to sense the world. And so the things we might use to do that include cameras or LiDAR. You may have heard of LiDAR, which fires lasers at the world and measures how long they come back to produce kind of a 3D view of the world. And of course, there's motor encoders, GPS, IMU, radar, sonar, all kinds of things. Other sensors that we can and do use in these self-driving cars. And then what do we do with that sensor data? Well, we have to do perception, and perception is really processing those things into a format that can be understood or consumed by other algorithms. And so things we might do is to take camera images and perceive depth, or we might detect objects, track them. So this is what perception at a high level is doing, and it can and does do much more than that. And then once we have perception and understanding of the state of the world around us, we also need to be able to look forward in time and predict what's going to happen. And so this is a small video of the visualization that I believe is available to those who own Tesla cars with the full self-driving system. As you can see, it's looking at lane lines, it's predicting the trajectories of other cars, it's predicting the locations of other cars, it's detecting stop signs, velocities, all kinds of things. And so the amount of information you need to really drive out in the wild is vast and very rich and complex. And so once you kind of understand the world and you can kind of predict what other people are going to do, we need to also devise a plan for ourselves of what we're going to do. And so that's an area called planning, where at kind of a higher level, we determine where our robot's going to go, how it's going to get there. And then we take those directions that are maybe geometric or a little bit simplified, and then we have to control our actuators using more, older, more mathematical techniques to get our car to travel exactly at a certain velocity, not to slip, and so on and so forth. And so these are kind of the high-level components of a self-driving car. And now to take a kind of a bird's eye view of the landscape of self-driving, maybe some of you are familiar with some of the efforts that are out there today. Of course, Tesla is always in the news, and then there's Waymo, which is another famous effort that's being funded by Alphabet, Google, and there's a whole other host of efforts working on this. And some of them are building their own cars. Some of them are using existing cars by attaching sensors on them. So there's really a big diversity and a lot of money, time, effort that's going into this. But one of the ways that industry looks at self-driving cars is using what's now a fairly well-established system of levels of automation by the Society of Automotive Engineers. So there's 5 levels, and I'm imagining some of you are familiar with this, but let's just go through it quickly. So L0, level 0 is no automation. So think your 1993 Toyota Corolla. It does what you tell it, and that's it. It's really not doing anything that you don't want it to do. It takes your commands and sends them directly to the steering wheel, the wheels, etc. Now at L1, there may be some small driver assistance features. There may be things like, braking or other small things to help you in ways that are imperceptible to you, but make sure that the car drives safely. Now, partial automation, I think maybe this is where the self-driving system in Tesla and a few other car companies have this now, where it's, you're having to pay attention, you're having to hold the steering wheel, and you're still mostly driving, but it's doing things like lane keeping, cruise control, maybe a little bit more than that. You have to stay engaged all the time. This is, in progress, and I think many companies already have this. It's unclear, where this is going or how safe it is, but it's out there in many different ways. Now level 3 is kind of a laughable concept, in my opinion. This is called conditional automation, and I'm just going to read the text there. The driver is a necessity, but is not required to monitor the environment. The driver must be ready to take control of the vehicle at all times with notice. And I think this is a disaster of a state, because I could be sitting in my car and you could say, hey, I'm driving, but the car is going to drive, so I don't have to pay attention. So I'm going to read the newspaper, I'm going to watch a video, and then you're going to tell me, hey, take over, there's an accident about to happen. This is really not going to work, probably. And then there's level 4, which a lot of companies, again, are trying to target, like Waymo, Cruise, which is high automation. This is kind of like saying, hey, there's a few conditions, maybe sunny days, wide roads, early morning, or maybe just parking, like the Tesla, auto parking feature. Anywhere where the car can say, hey, in these conditions, I've got it 100%. You don't have to worry. That's high automation, L4 automation. And finally, full automation is we drive all the time, anywhere, anytime. And this is also, as you'll see from some examples I'm about to share, hard to imagine. I mean, that everything is a lot, so probably not going to happen. And so to kind of color some of the challenges that the industry is facing, some of you may be aware that on October 2nd last year, the Cruise self-driving effort was in an incident where they were at a crosswalk. A car next to them bumped into a pedestrian. The pedestrian fell in front of the car, the Cruise vehicle, and the Cruise vehicle drove on top of that person and then dragged them 20 feet as it was trying to do a evasive maneuver. And this is an example of, to be fair to the folks at Cruise, this is very hard to predict that something like this would ever happen, and it's a big challenge to decide what to do. On the other hand, it's something that we expect as a car outfitted with hundreds of thousands of dollars of sensors and safety engineering, that we should be able to try to avoid this, or we should make sure we avoid this kind of thing before we proceed. And it's also the kind of thing that a human would deal with intuitively, maybe more thoughtfully for the most part than this. So this is one example. There's been other examples. There was an Uber collision much earlier where a person was killed because neither the car nor the safety driver saw the person. So, I think, it is time to step back and think about how fast this is going to happen, and what safety steps we might have to take before we proceed. And the reason for that is driving is very, very hard. Humans are excellent drivers, and the truth is we don't really know exactly how we're doing all of this. In order to drive, it's intuitive that we need to understand how the car works, the world around us, how people think and what they do. But at some level, it's also beyond conscious thought. What we're aware of is kind of things that are happening in the prefrontal cortex as we're a driver. There's lots of other stuff happening. And for example, you might have been driving and you've avoided a collision when someone's trying to merge. Some of that's happening without you even thinking. And of course, there's situations, many of you where you live, I hope the traffic isn't this bad. I grew up in Jakarta, and this driving in an intersection there can be kind of a coordinated chaos where the lights are kind of a suggestion, but people are sort of driving in all directions. And this is very tough to try to automate the system to handle this coordination between very large groups of people. And another example that might be a bit of a challenge is here. This is an intersection in Sweden where it's both a kind of a town square, but also there's 6 different lanes coming into it. There's no signs, there's no traffic lights. These are the kind of situations we encounter as humans, and we have kind of no problem dealing with it. The other thing that's very surprising, if you look at the data, is that humans are incredibly safe. It's really hard to fathom how safe humans are at scale. Humans drive trillions. I had to stare at that number for a long time. There's 12 zeros in that number. Trillions of miles every year. And even in the US, they drive a trillion miles, and there's 40,000 deaths that happen in the US over this mileage. Now that's not, that does feel like a lot, but for every billion miles, there's 7 deaths. And so what does this scale mean? Well, we can be very confident in how safe humans are. And by contrast, if you try to say, well, how safe, what percentage, how accurate do my algorithms have to be on a self-driving car? It's really shocking how accurate you have to be in order to get to the same level of safety as humans. Now, why does this matter? Well, one of the reasons I think we pursue self-driving is safety. That's one of the motivations. And so to get to being as safe as humans in all the different situations and over the mileage that humans drive is an astounding challenge. And so to give you a feel for what that means, if for every 10 seconds, the likelihood that you make an error is 0.1%. 0.1% sounds like that's extremely good. That's an extremely accurate system. Something dangerous would happen every 3 hours. And so it's really unfathomable the degree of safety or the degree of just how well a human can do at these things. And so you're looking at a really hard problem. And for a bit of a contrast or a context, air travel is the safest mode of transportation we have, and that's about 100 times safer than what's already very safe, which is human driving. And so what's the challenge? Why is it hard to get a self-driving system to do these kinds of things? Well, the dangerous things, they're fairly rare, and that's the whole problem. And so if we look at the distribution of events, so all the kinds of events that can happen as you're driving around in any city over the days, weeks, and months, call this a long-tailed distribution. And the reason for that is if you plot the frequency of an event over the event, it looks like an animal with a very long tail, if there's a dinosaur with a long tail. So the tail is all these random things that you would never expect to happen that do happen maybe once or twice. But then all the things that you're used to, just normal driving, they're happening all the time. And so trying to predict how much you have to drive, how much you have to practice to catch all of these things is a big challenge. We have some models to do that, but it's even if we use those models, the answer is kind of daunting. Like you have to drive billions and billions of miles before you can be, at all confident that you're ready for the world. And so some more examples of crazy things that self-driving cars have run into is a Waymo car ran into a telephone pole because there were too many in an alley and it wasn't really set up to do that. Another interesting one is a cruise vehicle drove into wet concrete because it kind of looks like a normal road, but that small shade difference in the shade of gray, that's the kind of thing a human might see, and it's a bit tricky to program or to think that you should program. And so for all these reasons, like getting a safety system, getting machine learning to be that safe, getting to that 10 to the negative 7 is a big ask. And so now if we think about one of the key elements, the key algorithms that has really powered self-driving robotics and so many other technologies is machine learning. And in fact, self-driving development or early development really pushed machine learning forward a great deal. Machine learning enables incredible capabilities that are otherwise not possible. Without some of the algorithms and technologies in that field, there's just no other way to do some of these things. But those of you familiar with, for example, a classifier, you might know that on ImageNet and some of these other large image classification tasks, good classifiers have accuracy numbers that are like 90%. And so you might think, hey, what if my accuracy is even 99%? Well, it turns out if you start thinking about this, suppose you drive for an hour, you have 10,000 frames of images that you've got to classify. How many of them might you be getting wrong? And now think about 1 billion hours. So you're looking at a ton of potential failures. So it feels kind of hopeless to use these systems without backups and other maybe redundancy. And so you could think, yeah, let's use them in parallel, let's use an ensemble, but it turns out you still need a lot of them. And so one of the common tools used to analyze the safety of a large complex systems, fault tree analysis, is used in aerospace all the time. When you have a subsystem consisting of a bunch of other sensors, algorithms that feed into it, if you know the safety level of each one and the degree of independence of systems working in parallel, you can kind of estimate the end level safety of the whole thing. And so it turns out if you just do the basic experiment that you say, let's say you have as many classifiers as you want that are 90% accurate and they're all independent of each other. They've been developed by independent teams. How many do you need to work in parallel to get to 10 to the -7? Well, it turns out it's about 10. So it's pretty demanding to use systems that are 90% accurate to get to the kind of safety and accuracy that you need to be as good or better than a human. And so now let's speculate a little bit. How do humans do this? I don't actually know the answer, but I can guess that humans really rely on models. We have a very simple, but a very general understanding of the world. And so anytime you throw a new situation at us, we can kind of estimate what's going on and be pretty good about it. We can also hone that estimation over time as we drive towards something. Our understanding gets better and better because we're getting more and more information. And maybe we switch models halfway through because we see something we didn't expect. So for example, say you're driving on the freeway and you see something that looks like a box. At first, from far away, it might seem like, oh, I should avoid it. It's dangerous. It could really hurt my car. But as you approach it, you kind of see it, moving in the wind, and you think, oh, okay, if it's moving in the wind, it's probably empty or it's very light. It's okay to drive over that, that kind of thing. And then here's another kind of interesting example. This is the Tesla full self-driving system driving behind a horse-drawn carriage. And you can see that it's sort of detecting it as all sorts of things that are sideways, a guy walking behind a truck, a sideways semi-truck, a backwards semi-truck. And understandable, again, the Tesla engineers are incredible, doing incredible work, but it's just something they haven't seen before. It's an exception. And so in this case, it's not a big deal as long as you know that there's something in front of you, it's fine. But you can imagine that, let's say you're taking a turn at a high speed and the thing in front of you is at the wrong angle. This could be catastrophic. And so another kind of wild example, former colleague of mine working over at Waymo was saying, they were driving around San Francisco and a person emerged out of a manhole and walked away. And so again, the kind of thing a human would say, oh, okay, that's a little weird, but I know what to deal with it. But a perception system in a self-driving car may not know what a manhole cover is. And so these are the kinds of challenges that we need to think about. I'm not sure if we need to deal with them explicitly, but we do need to think about them. And what would we do if our self-driving car came upon such a situation? And so to try to take another step back, self-driving and a number of the other efforts that are happening around the world today, it does help to step back and try to ask the question, what are we trying to do here? And so for self-driving, we can ask the question, what problem do they solve? I'm not sure if it's safety, because as we saw, trying to be better than a human it's not really a good business proposition. It's very hard. It might not be cost. Waymo car costs anywhere between $200,000 and $400,000 at scale if you're building millions of them. And it's an interesting exercise to try to do the math to compare that to taking Ubers 100% of the time, or other ride-sharing apps. It's a tough bargain to make money at this price. And it also might not be convenience because, at least for now, self-driving cars often will take routes that avoid, for example, unprotected left turns or busy streets to be a little safer. I think the reason that so many companies and so many folks are pursuing this so aggressively is that it's the promise. It's, well, if it works, it's trillions and trillions of dollars, and it would really change the world. And of course, that's true of so many great technologies. For example, if we had time travel, I'm sure it would make trillions of dollars. We would all use it. It would be fantastic. We go see the people we like, our loved ones in the past. Similar with quantum computing. So in that sense, it's a bit like a lottery ticket. How great it would be to win. And So again, for each of these cases, for safety, cost, convenience, we could say, well, if those are the things we actually wanted to solve, like if we wanted to solve convenience and access and cost, we would build more trains and buses and invest over the long term. We might say, there was 40,000 deaths a year. I wonder how many deaths we would avoid if we put a breathalyzer in every driver's seat. That wouldn't be, ignition doesn't start if it senses that you've had too many drinks. The other thing we can do is mandate safety sensing. So here in the US, backup cameras were not legally required until somewhat recently, and they prevent 100% of deaths where large trucks and SUVs back up over kids playing in the driveway. So this is regulation can really help. Similar story with seatbelts. Another motivation I think that would make a ton of sense for self-driving is research, broader research, where we're not really in a rush to make money or deliver robotaxis, but this is a hard, rich problem, and we're just trying to understand reality and build technology, and keeping in mind that progress isn't a straight line. And all sorts of technologies are built for one thing and used for another. And some of you may be aware that machine learning, AI, chatbots, everything like that today is powered by GPUs, graphical processing units. Those were built to play games and draw the pictures that appear on your screens, just drawing. And so it was kind of an accident that in 2013, a master's student at the University of Toronto was like, oh, let me try programming this convolutional algorithm on a GPU and see what happens. And lo and behold, it was fast. It was an accident. Similar story with the internet, which powers our whole life. ARPANET was a simple effort to connect a couple of computers and send some messages to each other. And they did not predict that it would completely change human life as we have today. So yes, we could work on self-driving, but maybe be open to different approaches, different ideas, different use cases, because it's hard to predict how these things work out 10, 20, 30 years down the road. And very briefly, I'll make an analogy from self-driving to AI. This is something that's top of mind for all of us today. AI models, these chatbots, generative models, they're basically they maximize the conditional probability of a completion given your query, and they appear to be intelligent. And part of the reason that they appear to be intelligent is often we ask questions to which we know the answer. And what does that mean? Well, we might change our query a little bit to help get the right answer, or we might also kind of squint and accept maybe small errors or small things about their outputs that we're sort of okay with. And so they're really fantastic for a ton of use cases. But a lot of applications that people are thinking about too require that the inputs may be very specific, never seen before in the training data. We might require accuracy in the sense that we have to correctly interpret the input and we have to get the right answer. And we might require logical reasoning as part of the answer. So you can look at this as control flow. Like if you ask a chatbot to write a program, there's a bunch of if, else, switch statements, while loops, things like that. And it turns out in that scenario, they're not so great. And there's a lot of different benchmarks or studies that look at this. One of them I think is very interesting is studies looking at AI models doing block stacking. So the block stacking problem is a classical problem in classical AI, which is a field that's existed since the 60s. The idea is that you give the computer a problem involving a pile of blocks on a table. Maybe there's a red block, green block, and blue block. And you say, the problem is, I want you to stack these blocks in a certain order, and you're not allowed to touch this block before that block. Turns out these kinds of problems are very easy for humans. You can give randomly selected humans across the world with different backgrounds and educations block stacking problems, and they're very, very good at solving them because this is the kind of basic logical reasoning that humans are fantastic at. It turns out chatbots are atrocious at them. And so I'm happy to share the references if you're interested, but they're okay at the version of the problem I mentioned, the red, green, and blue blocks, that's kind of shows up in a lot of text. And so they can be pretty good at that version of the problem. But if you change the words, instead of red, green, and blue, you say tall, short, and hairy or something like that, or you change blocks to other things, they basically get 0%. And part of this might be because it's conditional on what they've seen. And another very, I think, Important example is program correctness. There's multiple benchmarks where chatbots and AI models are asked to write programs given specifications, and they often struggle to get the programs correct. And these correctness is measured by running a series of tests on the output. The best models are under 90% accurate, and you can imagine if they're writing programs that go into things like your personal devices, where they're controlling the privacy of your data, or even privacy of data of big companies, the government. This could be catastrophic in many ways. And so, yeah, that leads us back to my takeaways. Mentioned them before, but I'll stop talking here and take any questions you may have.
Let's thank Krishna for that amazing presentation. I'm also going to stop recording so that we can take a few questions.